whiteboarding is the study of change. More specifically, we're going to be studying differential calculus, and we're going to be looking at rates of change. And we know what rates of change are with lines. We know what rates of change are with lines. We can find the slope, we can interpret it as a rate of change, right? But the problem comes into play with a curve. So, calculus helps us deal with that problem. So it's the study of change. If you think about a parabola, for example, there are parts to that parabola where if you were to draw a tangent line to the curve at a specific point, that tangent line would either have a positive slope or a negative slope, or, as in the case of the vertex, it would have zero slope, right? So we have an issue. We can't use the techniques that we are accustomed to from algebra to find or interpret these rates of change, okay? Now, the first concept that you need to understand when it comes to learning about this branch of mathematics that has to do with change is a limit. We've actually talked about limits before when we talked about converging sequences. For example, converging geometric sequences, if we have 2.001, then 2.01, and then we would say that it converges to 2. Remember that? We talked about how you could have an infinite geometric sequence that gets infinitely closer and closer to a number, arbitrarily close to a number, and that number would be 2 or 3 or 1.5, right? What we were finding then in our converging sequences was a limit, okay? Now, let's read this here. It says the concept of a limit is essential to calculus. It is based on the fact that you can get infinitely close to a value but not actually reach the value. And then they say, remember, sums to infinity. So, what happens to y as x gets really, really close to 3 for the function y equals x squared? Now, it is important to look at values to the left and to the right of 3. This is easy, right? We can plug in a number and we'll get an output that will be the limit, and we'll talk about that. But for now, take your graphing calculator, put y equals x squared, find a table, put in those values, write them down. And likewise, we're going to extend our table so that we look on the right side as well. So I'm just writing another table here. So fill in both for the left and right side of 3. So as x squared, as your x approaches 3 from the left and from the right, what is the value of your function? What is the value of your function? We get closer to what number? 9, right? That's called direct substitution, okay? So what we found was a limit. We said that, what is the limit? What number do you get really, really close to for the function x squared when you are approaching 3? And that number is 9. Okay. Now that's easy, but of course, with calculus and with limits, you can't always just plug something in and get an answer. If your function doesn't have a hole in it, if it's continuous, just like x squared or x cubed, then that's fine, you can plug it in if there are no problems within your graph. But as soon as we start dealing with discontinuous functions or piecewise functions, then we start running into issues. It is extremely important that when you're looking at a limit, you are evaluating the limit both from the left side and the right side. And the way we write it is like this. The limit on the left side and the limit on the right side have to be the same. If they are not the same, then your limit does not exist. So these have to be equal. And typically you can just write DNE for does not exist. Does not exist. Because the whole idea of a limit is what are you getting closer and closer to as you approach 3 from one side and 3 from the other side? Well, if both sides are going to different numbers, then you don't have a limit. Does that make sense? So they have to be equal. So 3 on the right is 3.01, 3.001, 3.0001, right? All of those values that are a little bit over 3. 3 from the left are all of those values like 2.9999, 2.99, 2.9 that are a little bit less than 3, okay? It is helpful because sometimes you will get problems that aren't just like your x squared to have your graphing calculator and plug it in on a table and look at the limits on the right and left side. Do we have any questions so far? And of course, when we say if something gets really, really close, we call that arbitrarily close. That's the word that you see often. Arbitrarily close. So there's a little bit of a typo here. So let me make this one correction before I start jumping in. This says, let me zoom in. If the value of x gets infinitely close to a value capital A, but not equal to A, then f of x has a limit of capital A. As x approaches little a, we write this as the limit as x approaches little a of your function is equal to capital A. All it's saying is when you're approaching a particular value, you can plug that in through direct substitution and you get a number out, and that is your limit. As long as, and I'm going to write this down, you don't have any holes, asymptotes, or you're dividing by 0, okay? So no holes, no asymptotes, no dividing by 0. Because then we get into trouble. We start dealing with indeterminate forms and things like that, which you're not going to deal with at this level of calculus. Otherwise, you can just plug it in. If it's x cubed and they want to know the limit as x approaches 3, you just plug in 3 cubed and you get your answer, and that's your limit. Okay? As long as it's a continuous function. Now, sometimes you'll have holes in your graph. So if we look here, and this is a small typo, let's rewrite this as the limit as x approaches 2 of f of x. The value of your function at 2 is equal to 1 because that value actually exists, right? We talked about this, or you've seen this with piecewise functions. You may not always have a value on your specific graph if there's a hole in it. If you're given other points, like we are in green, then that is the value of your function at that particular x value, if it exists at that point. So if you look here, this exists, so the value of your function at 2 is going to be 1, because this point is given to us. This exists, this does not exist. So your function may not exist, but your limit will still exist. Because what's a limit? What is the value that you're getting arbitrarily close to, or actually reaching on your graph, on the left and on the right? So even though my function doesn't exist here on this particular graph, my limit does exist, okay? So my limit of my graph as I'm approaching 2 is 4, but f of 2 is equal to 1. So in a nutshell, your limit, and I'm going to write this down, your limit can exist when your function does not. And vice versa. Your function can exist when your limit doesn't exist. Well, we're going to take a look at the end. I have 3 graphs that will make all this clear. Okay? So just bear with me for a moment. And then at the end, we're going to look at 3 different cases that will, I think, solidify your understanding. Now, I actually pasted this part of your book in here that I just want to read through because I think they do a really good job explaining it. So, they say that the graph of y equals f of x is shown alongside. It is the straight line y equals x plus 5. With the point 0, 5 missing, there's a hole in the graph. Your graph is no longer continuous. When it's not continuous, we can't use direct substitution to find our limit. However, even though this point is missing, the limit of f of x as x approaches 0 still exists. In particular, as x approaches 0 from either direction, you still get a limit of 5. So, in practice, we do not need to graph the functions each time to determine the limits, and most can be found algebraically with just directly plugging it in. It is important to note that in defining the limit of f as x approaches a, x does not reach a. It can with a continuous function, right? If it's a parabola, you can just plug it in. The limit is defined for x close to but not equal to a. Whether the function is defined or not at x equals a is not important to the definition of a limit. What is important is the behavior of the function as x gets very close to a. Is that clear? What are you getting close to? It's a different question than what is the value of your function. They can coincide, they may not. Okay. So for example, and then give you that example, if f of x equals 5x plus x squared over x, and we wish to find the limit as x approaches 0, it is tempting for us to simply substitute x equals 0. Not only do we get the meaningless value of 0 over 0, which is called an indeterminate form, but we also destroy the basic limit method. Okay, and we're going to start talking about piecewise functions here in a moment. Now, you can factor equations, cross things out, and remove holes. And that's what we're going to take a look at now. So maybe you try your direct substitution, right? And you get this. You don't want to graph it. It's going to take too long. You're trying to find the limit. You understand that it's the value that it gets super close to, that it may hit, may not hit. And you want to do it algebraically. Well, when you plug in 0, you get this, 0 over 0, which means nothing, right? So, what you do in this case to get this answer is you factor and cross things out. When you start factoring and crossing things out, you're removing the discontinuity. And we're going to practice that. It's a lot easier than it sounds. Okay? So, let's take a look. I'm going to go through these three with you. X squared is a continuous function. I'm not going to run into any problems if I'm finding the limit. I can just plug it in through direct substitution. So what is the limit as x approaches 2? What's the limit as x approaches 2 of x squared? 4. You can verify that on your graphing calculator using a table. You can say, what does 2.01, 2.001, 2.0001, and then what is 1.99, 1.999? What numbers do they get close to? And you'll see that it gets close to 4. Yeah? So now let's plug in 0 for b, the direct substitution method. 0 plus 0 over 0. Okay. Well, what's wrong with that? You get 0 over 0. That doesn't help us. You could graph this out. You could look at a table. You could say, okay, well, what about 0.001, 0.002, right? And then on the left and on the right side, and then negative 0.001 and negative 0.002. You could do that. Or you could remove the whole by factoring. When you factor, you can cross out those x's, right? And when you do that, you are left with this. When you crossed out those x's, you're removing the hole in the graph. It is a removable discontinuity, okay? Now, you can plug in 0 directly. And get your limit to be 3. And you can confirm that on your graphing calculator and see that it's going to give you 3. So why don't you try that now? Punch this function into your graphing calculator, look at a table, and confirm that it is indeed 3. And I'll pull it up on my graphing calculator too. Sean. All right. All right, let's take a look at this from your graphing calculator. Okay, so if you look at 0 on the left and on the right, you get 3.01, 3.001, 3.01, 2.999, 2.999. It's getting close to 3, right? So you can verify through your table that that is actually the limit of our function. If you directly try to plug in 0, you're going to get an error, right? Because you have a hole there. But if you factor and remove the hole, you can still find the limit directly. Does that make sense? Yeah. Now, what happens if what we're approaching is infinity and not a number? Well, we can still do direct substitution. And we can still look at infinity on the right and on the left. Now, you might be asking, how do you do that on a graphing calculator? Put in huge values. Look at 100, 500, 1,000. Look at negative 100, negative 500, negative 1,000. You're looking at what happens as you approach infinity and negative infinity. You can use your graphing calculator there. Now, looking at limits to infinity just takes a basic conceptual understanding of fractions. So they say we write x approaches infinity to mean when x gets as large as we like and positive. And I do not like the way your book writes it here. They need to put a plus sign. When you're looking at infinity from the right and on the left, typically you have that plus sign on the right and on the left if you're looking at there. So you could either write this or you can write this. For the sake of the book, we'll just keep it positive infinity, negative infinity. Now, let's take a look at an example here. If we look at the limit of 1 over x as x approaches infinity, that's 0. Because as you make the denominator larger and larger and larger, what's happening to your fraction? The larger your denominator in a fraction, the smaller the value, right? So as you approach infinity, which is, goes forever in one direction or the other, you're going to get smaller and smaller and smaller and smaller. Does that make sense? So if you have an x on the bottom, or even if you have something like this, think about what's going to get larger. Well, if the denominator, can you close the door for it? If the denominator gets larger at a much faster rate than your numerator, then it makes sense that your limit's going to be 0. Eventually, it's going to get so small that it's basically 0, right? Do we have any questions about this? And they say that here. X gets very large, the value of 1 over x gets very small. Questions? Okay, so you're sort of getting the hang of it, I hope. Yeah. All right. Here we are. Let's take a look. So here, we're just going to interpret this. It says, discuss the behavior of this rational function 2 minus x over 1 plus x near its asymptotes, and hence deduce their equations. State the values of the limit as you approach negative infinity and as you approach positive infinity. So they graph this, right? They find that vertical asymptote when you set the denominator equal to 0. They find the horizontal asymptote when you're looking at the ratio of the numerator and denominator. And then they're able to plot the graph, and you find, again, that your graph's going to follow the asymptotes. So we have that basic shape that we've used to graphing. Now, near its asymptotes, so near x is equal to negative 1. On the left, your graph is approaching negative infinity. And on the right, your graph is approaching positive infinity. So I'm going to stop and go up here and explain that. What this means is that when we find our horizontal asymptote, we're finding our limit as x approaches negative infinity and positive infinity. A horizontal asymptote is what is the limit as x approaches negative infinity and as x approaches positive infinity. Okay? So if on a question, on an exam, they tell you as x approaches infinity, f of x approaches negative 1, they're telling you what the horizontal asymptote is. Does that make sense? Okay. Now, not every case is going to look like this. So let's look at this example. Find, if possible, the limit as x approaches negative infinity and the limit as x approaches positive infinity. So, as x approaches negative infinity, so as we get smaller and smaller, and our x values, what's our y approaching? As your graph is getting more and more positive, what's your y value? 3. Are your limits the same on to negative infinity and to positive infinity? No. But that still doesn't mean that you can't use this to find a horizontal asymptote. So again, if they tell you that the limit of your graph as x approaches infinity is some number, not negative infinity, but infinity, that is your horizontal asymptote. Does this make sense? You may not always approach the same number with infinity. Now, if you are looking at a countable number, the limit as x approaches 2 or x approaches 3, you have to approach the same number on the same on both sides. Otherwise, your limit doesn't exist. But the point of looking at it in infinity is determining our horizontal asymptotes. Okay? Now, other than this little Mean Girls reference, if you've seen the movie, how many cats do you think you need? The limit does not exist. I've got this last slide here that we're going to just talk through. So let's determine the value of the limit and describe its relationship to the function. So what's the value of your function at 3? At x equals 3? Does it exist? It exists, but it exists down here. So if I want to say f of 3, let's just take a guess here. What do we want to say that is? Let's just call it 1. Does your limit exist as x approaches 3? So does, in other words, as x approaches 3, what's your limit? Does it exist or not? The value of your function at 3 is 1. What's the limit of the function as x approaches 3? Does it exist or not? So here, your limit does not exist because what I'm given is a piecewise function. And what I'm given, I'm looking at the left side and the right side. And as I'm going to 3 on this side, on the left side, and as I'm going to 3 here on the right side, I'm approaching 4 up here and 1 down here, and that doesn't allow me to have a limit because I have to approach the same number. Does that make sense? Now, what's your limit for the next one? Let me zoom in. First of all, does your function exist at 2? Your function does not exist at 2. So f of 2 does not exist. okay? But your limit of your function as x approaches 2 does exist. What is it? About. Yeah, let's just say 7. Okay? Because again, what am I getting super, super close to? I'm getting super, super close to 7. I don't exist at that point. A function doesn't exist at that point. But you could factor it, remove the whole, and still directly substitute to get your limit. Okay, last one. Okay, what's the value of your function at 2? What's the limit as x approaches 2 from the right and the left of your function? About. I would say a little bit less, maybe 0.75, or let's just say a little less. Does this make sense? Do we have questions? 0.75 and 0.75 are the same thing.